Today we're dealing with a ceiling function, folks, an equation involving a ceiling function. Let's just do a quick example of what we mean by ceiling. Floor is a little more popular. It's sometimes called the greatest integer function. The ceiling is sometimes called the least integer function because it's the least integer that's greater than the input argument, as this definition indicates. Let's do a concrete example. Let's say something easy I can compute here, 27 over 13. Now, notice this is just a whisker above 2, right? But the ceiling function sends you to the next integer. So this would be 3, okay? If this were the floor function, it would be 2, of course, okay? But that's because that we have 3 minus 1, straight from the definition here, strictly less than 27 over 13 less than 3. Less than or equal to, sorry. Okay. Now, a very useful fact for solving this problem, which turns out to be quite easy, in fact, we can just rewrite, this is the object we're dealing with here, right? So we can rewrite it like this, and it's in this linear form, okay? So it's really a piecewise kind of linear function, like it would look something like this if you were to graph it. Now let's put 1 here, okay? 1 and 1. See, it would just be the line 1x from 1 to 1, right? That's very clear, right? Since the ceiling of any number between 0 and 1 is just 1, this is just the equation for x. But now, if you move over to 2, it's going to go all the way up to 4 up here somewhere. This is not very good, but we'll say that's 4, right? And so you would have, and it's not scaled very well at all, but it would look more like, something way up there, okay? And the slope of this line would be 2x, and I've done a piss poor, but it would be a steeper. This is x with a slope of 1. This is 2x with a slope of 2, right? And the thing goes up, again, I haven't done it much justice with that half-assed picture, but you get the idea that it is it's sort of shaped like a parabola, which is believable since this is about like x squared, right? But in any event, what will happen right here is you need to do some arithmetic to determine that 444 over 13 is between 34 and 35. And that implies that C would have to be 6. In other words, it would be the 6x function, okay? The 6x function, if you just look at this definition. In other words, it would correspond to the 6x function in that interval, right? Just based on what we've seen right here. Okay, so all we have to do is just equate this with 6x. Okay. Again, it is a piecewise function, and when you're in this range of numbers 6x, that would be from 30 to 36, right? That means your ceiling, that would mean this would be the function corresponding to our original equation, but that just leads to the trivial division by 6 right here. So what do you get? Is it 74? Yeah. So you would get 74. 6 times 74 is 444, right? Yeah. 420 plus 44. So this would be 74 over 13 equals 6. And equals x, duh. All right. Now, y'all notice it would be fairly close. This is kind of like more or less the discrete version of x squared, really. So if you said x squared equals to 444 over 13, you would get an answer pretty close, would be my guess, because this is close to x, it's within 1 of x always, right? So you may want to work this out and see how close you get to 74 over 13. And again, sorry about not, so this is the answer right here to the question. And again, you can use the graphing utility to see this graph a lot better. It's just a bunch of steeper and steeper lines. This interval would be 2 right here, and 4 is way up here somewhere. And of course, this would be a steeper line. I made it somewhat steeper than this version of X down here, but it's kind of fun. And you have discontinuities all the way because of the way the way it's defined. Little tiny, I guess they call removable discontinuities, but that's not important as far as the nature of this problem. So anyway, that does it. Thank you for viewing.